All right, let's get this show on the road. Can everybody hear me? I sure as hell hope so, because there's like a 30-second delay on this motherfucker. So, I'm Chili, and we are back for another session of designing our own CPU, which now has a name, by the way. The name. Wait, let me do the big reveal here properly. The name of the CPU. That's not the fucking Logisim. There we go. Is the chili pork unit, of course. I'm pretty proud about this. All right, thanks Volt. We're all good to go. All right, so let's just get right. Well, first of all, I wanna show you guys one thing that I did that I'm proud of. I made a little thing. What do you call it? Spreadsheet here, and it has all of the control words for every instruction and every phase of every instruction. So this should help out a lot when debugging or just other miscellaneous bullshit. And I'll link to this in the page with the downloads. And yeah, you guys can, if you want to refer to this at any point in the future, you will have access to this file. But it's very simple. Here are the control bits for every instruction here. So this is the register to register move. This is the immediate to register, phase 0 and phase 1, and so on and so forth. The colors just mean red means that is dependent on the instruction. So that bit is encoded within the opcode. And blue means it doesn't matter, no one gives a fuck. Green means that it is actually being controlled by this thing here. So green is only for phase 0 instructions. But that's not going to be around there for too long. There's going to be changes brewing. So anyways, yeah, this is, I don't know, I think this is pretty cool. And we'll make use of it perhaps later. Perhaps not, but it's there. Just know that it is there. So, last episode, what we did was we added the move register into memory instruction. So register to indirect, I believe. And that would be this one here. I got them mixed up and bullshit happened, but yeah, this is the one we added last. Move register into memory. And when we execute that, it crashes the entire CPU, which is, generally not what you want. So let's load a little program that I have prepared here. And it's very simple. It puts the address 0C into register B, and then it loads the data from that address into register A, and then it stores. Then it loads address D into register B, and then it again stores the contents of A into the memory pointed at by B. So, which is D. It's too many letters. Anyways, you'll see what happens when it happens. So let's try this out. I'm gonna zoom out, I guess, a little bit here. Yeah, we can see that. I hope. So first thing first, we're gonna make sure that we're on the Logisim screen. Good. We're gonna make sure we're gonna get our CPU into a nice stable state, and then we're gonna clock. So we clock up, we clock down, we clock up, and we see that 0C has entered register B. Again, we clock up. Now we can see that our memory is being accessed to address 0C, and down and up again, and now that value has been loaded into A, down, up, and down, up, and D, the value D has been loaded into register B, and down, up. And now we see that memory is now being accessed at address D, down, up. And so we see that the value was stored, so the operation completed successfully, but now the CPU has crashed and is no longer usable. So why does this happen? It's interesting to look into that. First, let's clear the CPU, and I'm going to reset the contents of this piece of memory. And we're going to single step through this bullshit here. So reset the CPU. Clock. there, down. And now before we clock this one up, we are going to disable the simulation. Then we're going to clock up. And let's zoom in a little bit here. Let's take a look at what happens when we single step through the simulation. So, I'm trying to think where the problem is going to occur. Well, let's do Control I believe single steps. Let me just make sure. Yeah, Control I, step simulation. So Control I. First thing that happens is the clock signal reaches these clock signal inputs. Then these guys, change their values depending on if they had values to change. Then this changes. And here, we now see that we're getting errors. So that's probably going to be because, let me think. This guy is changing. So this guy turned on, and I'm not sure, but I believe probably this guy still hadn't turned off. Or what? No, this guy turned on. Yeah, so this guy is still turned on, but this guy turned on. So now they're both trying to drive these lines here. And the problem with that is that they're driving the load line to different values. That's the main problem. Because, let me just step into that, driving the load line to different values gives you an error, and an error in the load means that the output of the memory is also going to become error. And once we get error in here, it's all over in phase 0, because this is going to pipe directly into here, and that's going to get us errors, into here. And once that error hits here, it's just going to be a feedback loop of errors. And there you go. So that doesn't work. Now you might ask yourself, well, I mean, why didn't that happen for any of the other instructions? The first two that we did, or 3 depending on how you're counting, they worked fine. And the astute of you might realize that one of these things is not like the others. One of these things doesn't belong. So for all of the instructions previously, we had been setting load memory to 1, which is the same thing that it is set to out of here. So there wasn't ever any error because both drivers were trying to drive it to the same value, and that's fine. The only time you get an error is when 2 outputs are trying to drive the 2 different values. So the problem only occurs because now we're transitioning from a state of driving it to 0 to a state of driving it to 1. So what I did was, when I first came across this problem, wait, why did I bring that up? Here we go. I thought about it, and I figured there's got to be a way to make this work. Obviously the simple way to do things is to simply connect this to the latch, and then have the latch directly drive these lines here. So don't go through the multiplexer. But the multiplexer's job is to give us access to the opcode in phase 0. If we do it through the latch, then the first phase we're not going to be able to do any work. And that's not a problem for these instructions here, or not this one, this instruction or this instruction. Because the first phase you don't do anything anyways. You just wait for the memory to become available so that you can make your transfer. So it doesn't do anything bad for this instruction or for this instruction. It doesn't do anything bad for the immediate move, but it does fuck with our register to register move, and it makes it 1 clock slower. And I didn't want to do that. But then I thought about it, and I'm like, well, I don't think I have a choice, because I don't want to deal with this fucking feedback loop bullshit. I know it's going to come up again. Even if I find a way to fix this problem, there's going to be another problem when I add a new instruction. So in the end, I said, you know what? fuck it, it's not worth it. Life ain't worth it, and I got rid of the multiplexer thing there. So say goodbye to that because it's never coming back. And I figured, well, I mean, most instructions, or many instructions anyways, are going to be working with the memory. We don't have that many registers to begin with. So it's probably not going to be a big deal if I, don't have, one clock cycle instructions for register instructions. It's not going to be the end of the world. But I don't know. I still wasn't happy about it. So you do it like this, and doing it like this means that you would have to move this instruction over here, right? You'd have to have a wait state for this one as well. And it would have to be executed in phase 2. In fact, you could just get rid of all of these phase 1s here and replace it with just a blanket state up here that does one thing, because every phase 0 now is going to be exactly the same. It's just going to be load the opcode into the instruction latch, or whatever you want to call it here. But what I figured out, clever girl, what I figured out was I can have my cake and eat it too. So let's take a look at what's happening. So before, what we had is a situation like this. I'm going to just draw a quick timing diagram here. Maybe something like this. I don't know. Yeah. So for example, for the register to register transfer instruction, here is where work is done. So this is register to register move. You do your work on the rising edge. That's what it's called, the rising edge. And let's see another one here. So here in our let's see, what is this one? Immediate into register. Here you load opcode, and then here you do your work. Seems fair. Now, this is for, with the multiplexer. Now, with the direct latch, you can't just do your work in the first clock because you don't have the opcode available to figure out what job you're supposed to do. So the first one is now going to be, load op and then work. And this one's just going to be, ditto. So this doesn't change here, but now your register takes 2 cycles. What I thought, and what does work is you can do this. You make your latch, your instruction latch, sensitive to the falling edge of the clock. So now you do your load operation on the falling edge, and then on the rising edge you're free to do work, because once this operation is loaded in this region here, it's going to become available to the instruction decoding circuitry, and so you'll be able to do work on the rising edge. So by making your latch falling edge sensitive, you can gain a nice performance increase there. And it's actually very common to have circuits that are, some that are falling edge sensitive, some that are rising edge sensitive. So basically what that means is that they are 180 degrees out of phase with respect to each other. And CPUs will often have more than that, so they'll have different clock signals that are out of phase with each other. But we're not going to do that. We're only going to have rising and falling. That's enough for us. All right, so this stuff is no longer necessary, but we do have to be able to control the loading of the latch. But I think the latch is only going to be loaded from where? From phase 1, right? So we can do that like this. Why are you incompatible with? That doesn't make sense to me. 8. And well, let me zoom in here. There's something wrong here. Zoom in. I think maybe I've got something backwards. No, this is data and this is enable. Why? I can't see shit because it's all fucking small. Incompatible widths. I don't get that. This doesn't seem right. Maybe someone can tell me if I'm being retarded, but yeah, it's probably just my simulation is not enabled. No, that doesn't do it. Reset simulation. No, that doesn't do it. Ah, okay, thank you. Thank you, Hydrovolt. I think that is probably what happened. Yep, okay. Whew. Thank you. That saved probably like a few minutes of me just fucking around trying to figure out what went wrong. This is why live streams are good. Okay, so there we go. Alright, so we enable it only on phase 0, and then it always loads phase... Wait, let me think here. Yeah, that's fine. Loading on phase 0 on the falling edge of the clock. And on the rising edge, we're able to do our magic. Now, that means that we want this to be driving it only on the falling edge. Well, let me think here. Yeah, we can leave this the way it is right now. It doesn't have to change. There may be changes in the future. I think this might work just as it is. I'm not sure, but I think this might not require any further modification. Let's load our little test program here and see if this fucks up horribly. All right, so we clear. Okay, clear. That's the first step. Good. Then we... Oh, wait. All right. Now, here's the thing about this circuit here. It has to start on a rise. It has to start on a high clock. If it starts on a low clock, you're going to get an extra instruction executed before it's loaded. So it's going to instruct, or it's going to execute opcode 00. No matter what you have here, it's going to execute. I'll show you later. I will demonstrate this, but just know that you have to start on a high clock, and we'll fix that later. So we go low, and that loads the opcode into here, and then high, and then low, high. All right, so we loaded that in there. That's good. High, low, high. Yeah, we load that into there. So far, so good. Low, high. High. We load the new address into here. Low, high, low, high. And we store that into here, and our CPU still has not fucked up. So, I don't know about you, but I think that's pretty fucking sweet, because we managed to fix all of our feedback bullshit, like, forever. Never have to worry about that shit again. And we didn't even have to sacrifice any cycles. So yeah, you can use the falling edge of the clock, and that will make your life easier. Alright, so what else do we want to do here? Well, first off, let's replace these inputs here with proper... I've been meaning to do this for a while. But let's replace them with proper inputs. So what we want here is we want a button on the clear, and we want a clock. Where is the clock? Wiring, maybe? There we go. We want a clock on the clock. So now this will allow us to, well, having a clock on here is good because we can simulate, we can set a tick frequency, let's say of 4 hertz. Let me clear this here. And then we can enable that, and it will automatically cycle and run like, a normal CPU, which is what we want. We don't want to be, clicking that fucker like fucking cookie clickers. We want that shit to go automatically, and now that it will because it's a clock. What else? Yeah, and obviously, I mean, if we want to eventually run this fucker at like 4 kilohertz, so we're not going to be able to click that manually. And this button here is just easier, just one push and reset the circuit. So nice to have. But now the thing is we want to make sure that no matter what state the clock is, whether it's high or low, we want the CPU to execute the proper instructions. Because if we started executing from here, let's just go tick frequency 2 hertz, and let's go ticks enabled. You see, it loads the address into A instead of into B, which basically fucks over our entire program. So you, as the circuit stands right now, you have to start your clock on the high state, and I don't like that. I think I want my computer to be able to start no matter where the clock starts. So this can be solved rather easily with a little bit of logic. So what we're going to do is we're going to add in here a little piece of memory, a little flip-flop here. And this flip-flop, should it be a set or reset maybe? Or a D flip-flop? I'm thinking set reset flip-flop here. All right. And what we're gonna, no. It's gonna be a D flip-flop. It's gonna be falling edge sensitive, and the clock is actually going to be hooked up to the clear signal here. And I don't know if this is the best way I could wire this up. But I'm sure Robert will wire it up a lot prettier afterwards. Anyways, what we want to do is, so we're going to put the input of the clock into the data here. So now when we release the clear, this is going to acquire the current state of the clock. And what we want to do is we want to make sure that when we release, the output from here is always starting high. So we need a little bit of logic. What kind of logic do we need? What we want is we want to compare. Let me think here. All right. I'm going to change this a little bit. I have done this once before, but it was like many weeks ago. All right, so this goes into here to remember the initial state of the clock. And then this is going to also drive the clock signal. But what we want is we want to invert this if we need to invert it. So inverting is generally done with what gate? The exclusive OR gate, or it's negative. And we'll just pipe that into there. All right, so let's just try this. And we see that if this starts high, this is going to be low. This is not what we want. Because if this starts low, low. So this is the exact opposite of what we want. This is the kind of design that I call not even thinking, just trying shit until it works. And I also like this kind of design. Okay, so we want to negate, what is this? No, we don't want to negate. We want to change this into a exclusive NOR gate. Here. Do that. And now, if our clock is low, it's going to start high. And if our clock is high, it's going to start high. So now we can ensure that no matter what state our clock is in, when we clear, we're always going to be starting on a high. And that is good for us. All right. All right. So, just a little bit of clock modification bullshit there. And now we are ready, sort of. But here's the thing. I can actually make this, what do you call it here? This fetching pipeline, or whatever you want to call it, I can make it faster. I can make it so that these instructions, these memory instructions, can also execute in a single cycle. Let's go back to our little diagram here. So what we've got so far, let's take a look at one of those memory axes. Hello, I'm sorry, I can't say your name. Is that what's the name of that? Cyrillic? Acrylic? I cannot read that. But hello nonetheless. I am happy to have you here. Oh fuck, I just deleted all that. So let's draw some more timing diagrams here. So let's see here. What kind of instruction are we trying to do? Well, let's try the registered immediate. So currently what we have is on the down beat, we've got our load op. And on the up beat, we have nothing. And then down we have nothing. And then up, we have work. And I'm thinking to myself, there's got to be some way to squeeze this in here so that I can get this all done in a single operation. Because before, sweet. His name is Chris. His name is Robert Paulson. His name was Robert Paulson. Anyways, what we want to do here, or what we had been doing, pardon my French, is we had to separate these into 2 clock cycles because first rising edge was load from memory and the opcode, and the second rising edge was then do the work, transfer from memory into register. So we can't squeeze these into one single cycle because, like I said before, we're loading from 2 different addresses here. We can't do that in the same cycle. So we had to split it up into 2. But now, the loading, the opcode for memory is done on the falling. So I want to be able to do my work here. And at first glance, you'd think that doesn't seem too difficult. But the problem is that for the instruction, what is the instruction? Let's look at the instruction table here. Opcode, go to Chrome. For the instruction here, move immediate into register, there's actually 2 bytes. There's the opcode, and then there's the immediate value which follows it. So we have to increment, in this instruction, we have to increment our instruction pointer twice. And that's a problem because, I mean, we don't have twice to increment. I mean, like, look at it. Let's look at this mother. What options do we have? We have rising edge, we have falling edge. Either way, we're only going to get one of these in a single cycle. So we can't increment this motherfucker twice. It's not in the books. It's not in the cards, as they say. So the question then becomes, well then, how do we do this? How do we do this bullshit, Chili? And the answer to that question is we're going to cheat. We're sort of cheating. Not really. But I mean, generally what I might want to do is have 2 clock signals. One clock signal that runs the entire circuit, and then another clock signal that's running at twice the speed, and that only drives, like, for example, the instruction pointer. And CPUs, they do run like that. Like, the internal logic areas will run at higher clock speeds than, like, the external clock speed. But we can't do that because we have a limit on our clock speed here of 4.1 kilohertz. So if I make the IP twice as fast, that means my machine is now going to run at 2 kilohertz because I can't go, my maximum clock speed is 4.1. So that's not in the cards. But we can do some little bullshit and double our clock speed. And the way we're going to do that is, let me just add a circuit here. I was going to say clock, and then I lost the L. And I'm just going to go with that. So, what do we have here? Alright. So let's just put a standard register here. And T flip-flop, D flip-flop. It's all the same to me. So we're going to stick this in here. And what are we going to do? We need something into there. So I will just put a standard input pin here. Is this a toggle? It is a toggle. Alright, well, we'll set this to power, I guess. So this will toggle every clock cycle. And there. Make it rising edge active, I guess. And so, work this guy. So high, low, high, low, high, low. There you go. It toggles every clock cycle. That's what it expects. That is what we expects. Now, let's do this a little bit different. What we're going to do is we're going to add in here a gate. We're going to add a NAND gate. Gate size narrow. I don't want 5 inputs, I want 2 inputs. There we go. I'm going to put AND gate into this clock here. And we're going to make this line drive both of the inputs of the AND gate. I didn't want to do that. So like this. So what do we expect? Well, hopefully we expect the same thing, right? Wait. I don't want a NAND gate. Sorry. Brain fart. I want an exclusive OR gate in here. Yeah, there we go. So what do we expect? Well, we expect this one to never go high because the 2 inputs are always the same. So this is pretty useless, right? But now, let's make a little change. We're going to add a buffer in here. Now all a buffer is it just takes the value in and it puts that same value out. So you might be saying, well, Chili, that seems like that's pretty fucking useless. I mean, you could do the same thing with just a fucking wire. But look at this. Oh, wait. Shit, this is not going to display what I want to display. Sorry. You won't see anything. We'll just forget that I did that. And we're going to put a different thing in there. Fuck you. We're going to put in here where's a counter? Memory counter. Here we go. All right, put a counter in here. So we want our, well, let's just connect this to here. This is our clock. This is our count signal. And, okay, good. Now, if I clock this, we're counting. Excellent. And I do want to be able to reset this. So, don't worry. This is this bit of fucking around does have a point. Just give me a second. Where's my buttons? There we go. Okay. So reset this. So we can count this, obviously. 1 count per clock cycle. Now, if I wire my clock from here, we would expect nothing. But wait. Now, every time I go up, 1, down 1, up 1, down 1, up 1, down 1, up, down. So in 1 clock cycle, which is 1 cycle of up, down, I'm actually counting twice. So I've just doubled my clock speed. Magic. Chili is a magic man. Anyone have an idea of how that works? Because I'm going to show you. It's pretty sweet. Basically, and it doesn't work if you take this buffer out, by the way. You get nothing. You lose, sir. So why does that, wait, let me just do this here. Why does that work? Basically, if we take a look at the timing diagram of this circuit here, we can see what's going on. Yes, the buffer is a delay. That is exact. That's the only thing it does. It is a gate, and so it has, in the simulation, it has a one-step delay. Yep. So what happens? Yeah, it's red. I don't want red. Actually, I don't want any of this bullshit. Is we've got our exclusive OR gate here. We got one input there, and then one input is being buffered into here. So if we look at the timing diagrams for this, for the two inputs and the output, and this input here. So this input, say it looks like this. All right, I'm going to run out of room, aren't I? That's a problem. Let's quickly move this up here. Good. Let's just, let's get professional here. A, B, C, D. So here's A. So B is just going to be the exact same thing as A, because that's just the wire hooked up to A. That's the input. Fuck, I'm going to run out of room if I don't use my space more responsibly. So there's B. C is going to be the same as B, only it's going to be a little bit delayed, right? Because B is going directly in, but C here has to propagate through this buffer. So it's going to look like this. And that means the output of D is the exclusive OR between B and C. So let's go A, B, C, D. So the exclusive OR here, in this region, they're the same, but in this region here, they're different. Then they become the same again, and then they become different, and then the same, and then a little different, like that. So as you can see here, now this generates a pulse for every transition here. And a pulse has a rising edge and a falling edge. So it's guaranteed, every transition of A is guaranteed to generate a clock on anything connected to D. And that is the magic of the pulse generator, which is this guy. And we can use this guy to double the clock signal. So let us do that. Where's my freaking where's my, there it is. ALU, don't want that. Computer. There we go. I don't want this. Please get off my dick. There we go. Better. Okay, let's zoom out here. So we want to double the clock signal for only the instruction pointer. So we're going to go into here and get rid of that. And we're going to add, let's just zoom in a little bit. We're going to add in a exclusive OR gate. Right here. That fits just perfect. To there, and we're going to add a buffer. Generally, you'd probably want to add like a few buffers because nobody's in the house. Papa bless. Alright, Papa's not here. But anyways, so normally you'd want to add a few buffers here because you might want your pulse to be a little bit longer. Because circuits might need some time to respond to the clock. There might be a hold time here requirement for the circuit. But in this simulation, we don't have those requirements, so I'm just going to put in one. Because the less gates we have in our circuit, the easier it is for my computer to simulate this and the faster it'll run. You might ask yourself, you might ask me, well, Chili, why don't you just, if you can double the clock signal, why don't you just double it right here for everything and make it all faster? And unfortunately, that's not going to work because why? Now I'm looking at chat and nobody jabroni is making me guess their name. I don't know, man. Kiefer Sutherland. I think Kiefer Sutherland would really enjoy a little logic design in his life. But anyways, so the reason why we can't double the whole clock is because my computer won't be able to run the simulation that fast. So we won't actually get any extra speed. It'll just slow down each clock. Because I checked my CPU usage, and I believe at 4K it's pretty much maxed out. So trying to run these circuits at 4K is not going to work, or at 8K or whatever. But running just one instruction pointer, one flip-flop at that speed, or I guess one counter, shouldn't be a big problem. So we can double pump this guy, and it shouldn't have a big impact on the performance. But the whole circuit, I don't think that's really viable. All right, so here we got this guy double pumped. Now we've got the problem of trying to revamp our circuits to use this. Because now, first of all of these guys can all run in a single clock. And second off, this guy can now increment in both the rising and the falling edges. So we need a way of governing all that bullshit and making sure. I guess it's not Kiefer Sutherland. I'm disappointed. But that's okay. So now the problem is that I have to think. I don't like that. I'm not good at that. What I want is this guy. I have the feeling that this guy. Hey man, I'm disappointed too. I was expecting Kiefer Sutherland, and I did not get him. Maybe you're the guy from The Walking Dead. What's his name? The guy that's teaming up with Kojima? I forget his name. Norman Reedus. That's his name. Are you Norman Reedus? Because that would be all right too, even though I don't really watch the Breaking Dead. I did watch season 1. I thought it was pretty good. But I'm getting off track here. I guess I could just try a bunch of bullshit and see what sticks. I feel like this guy right here, this is not going to fly anymore. It might only fly for, this is really only going to work now for, my brain started working again, and it's glorious. This is only going to work for the first half of the first phase. So for the part of the phase here, let's get the proper layer selected. I don't know who Cave Johnson is. It's a pretty good name though, I will admit. It's a strong name. Throw science at the wall and see what sticks. Yeah, that's good. Only my specialty is less science and more just throwing bullshit at the wall and seeing what sticks. But same idea, I guess. So here's what we got. You're the troll. I'm guessing that means that you're put pixel, but I could be wrong. Okay, so here is the region where we're loading the opcode into there. So here, this has to be fixed. But after that point, here we don't want it to be fixed. We want to be able to select this because now we're going to be accessing the memory in the first clock cycle. So we can't have I'm still in Chrome. That's bad. We can't have this guy driving the memory lines for the entire first clock cycle because we want to change those lines. We want to change what's driving the address so that we can, do stores and loads. So this is no good, but it's almost good. All we need to do is tie this to the first phase and I knew it. Master Sleuth Chili has once again been victorious. Unless you're being, sarcastic. Alright, so we want to combine. Why does this have 3 inputs? That's stupid. You should not have 3 inputs. Okay, one of these guys has to be negated. We'll make that one. So if we're in the 0th phase, and if the clock signal is low, then we want to drive this guy. So we only want to drive, it's got to be high. Shit. No. There we go. Yeah, because we start high. So we just need a simple AND gate here. So we only want to use these driving lines for the first half of the first cycle. And that'll work. Now comes the hard part. So this is all just about loading this guy. And then after that, it's all pleasure. So how does this work? This should be able to stay the same, I think. This, maybe we just move this over here. I'm thinking this could be easy. I'm going to save it. I'm just going to save as stream 69. There we go. And what we're going to do here is get rid of that. Now I hope this works, because I don't want to change all this bullshit. Yes. Okay, and we can just put this guy, maybe. This seems wrong. We need an AND gate here. Yes. Copy, paste. Move that over here. Face down. Don't connect to the fucking derp. There we go. Okay. Just fuck. Why are you? Why are you? Okay. Shit's getting really messed up here, but it's okay. I think this will work. Please tell me if I'm doing something incredibly stupid, because it's highly likely at this point. But here we go. There we go. Okay. So I'm no. I'm thinking this is probably acceptable. But I really didn't think it out too hard, which is probably not a good idea. Doing any kind of engineering, not thinking is what generally gets me into trouble. All right, so let's reset the circuit, and Control K will clock our thing now. That's the other benefit of putting this guy in here. You can use Control K to clock your thing. So we go K. Well, no. Oh, Control K starts the fuck. That was wrong. That starts the ticks. It's Control T that toggles the clock. Okay. Sorry. Let's try this again. Wait, now we got... I don't like you being there. Particularly. I don't like you being red. Why are you red and you red? I don't like that. Clear. It's not clearing. Alright, this might be a problem, but could be fine. This guy is often red and it doesn't really matter. As long as these enable signals aren't set, but they are, for some reason, they are not connected. simulation. Reset simulation. Clear. It did work. Okay, well, it's a little bit, what's the word I'm looking for? Scary. But we're going to ignore that for now. Let's just go Control T. Fuck. Reset simulation, also reset my program. Okay. Load image. Gonna load our program. And we are going to, once again, just make sure we're in a good state here. Let's go. Control fuck. Control fuck. Can't find that key. Control T. All right. Toggle. Toggle. Yeah. Yeah. Good. Did it work? Did I load something? Yes, I loaded C into B. Yes. 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 Okay, well, the other instructions shouldn't even work. Why am I doing this? I didn't set them up yet. Of course they're going to fuck up my CPU. Anyways. Let's simulate reset simulation. Okay, so this appears to work, right? And it's not super surprising, but I'm happy nonetheless. Now this guy, probably same thing. I'm thinking same thing. Just like move this over here. Let's try that. So we do that. We get rid of this. And then we try to move this over to here. And let's do the same thing down. Let's just test this. Wait, which one is this? This is the fuck. This is the fuck. Okay, we can always just control Z. It's fine. It's fine. Let's just do it. Do this one too. This guy over here. And now. Clear. Good. Yeah, shit. Load image. There. Okay, let's see if this motherfucker works. Can I get everything in? Yeah, I can get everything in there. That's sweet. Okay, Control T. Okay, so that works. We already established that. And then this guy works. And, uh-oh. Okay, it's a little red, but we're still maybe okay. Nope. Nope. Not okay. We did not load this part into here. Okay, so something is wrong. Something is not good. Oh. Oh, I know. I know what's wrong. Okay, so anyone care to guess what's wrong? The problem is, wait. I was like feeling all smug, but now I'm questioning my smugness here. Yeah, I think the problem is this guy. These guys are trying to drive the control lines at the same time that this guy is trying to drive them. Because these guys, the basic contract, the deal was that this guy drives it for the first half of the first phase, or the 0th phase, and then these guys drive it for the second half. But yeah, so that's why this guy works, because he's not trying to drive. Wait a minute. Why does this work though? Because if this stops driving it on the second half of the phase, then nothing is driving those lines. No one's driving the bus. Oh, okay. So this is register to register. We're not using that instruction, and that's why it was never a problem. But we have to do this now. So we have to connect these mothers. All right. So the reason Yeah, we have to adopt it. That's correct. The phase 1. That was the assumption. But I was just thinking, where exactly the problem is. No, you're not wrong, Hydrovolt. It's just that the exact problem was that originally these guys thought they had the whole clock phase to themselves, but now they only have the half of the clock phase. So they've got to take that into consideration. Now the reason why it didn't fuck up was because it just so happens that these guys were trying to drive it to the same line or the same values as these guys. But once you try to store to memory, now you're driving it to different values. You're going to collide with this guy. All right. So the way this works is, first of all, now everything has to drive those lines. We can't have any disconnected portions. That's rule number 1. Rule number 2 is for the first phase, phase 0, this can only go active in the second half of the first phase. So what we want to do here is basically just put an inverter into here. Where's my inverter? Not gate. Where's my not gate? Why can't I find my... There it is. It's on the top. Why is it so big? All right. So now it's saying these guys are basically mutually exclusive. Either this guy is going to be high or this guy is going to be high. Never both. And that's always good, right? So that's part 1 and part 2. Part 3 is we actually have to set these values. Now, I believe that this is correct. Yeah, low, low, high. Yeah, I think it's probably correct. I'm not actually going to check. I'm just going to test it. I'm not actually going to think and do work. So these guys, they're set because they originally were already driving their lines. So we don't have to worry about changing these numbers here. And this guy had the numbers in there from the beginning, so he's fine. This should work. I'm going to say this is going to work. All right, so we want to do maybe... Okay, so we're not in a bad state. I shouldn't have to reset this. Famous last words. Okay, reset the simulation. And then load image. I feel like I'm missing something now, because that's not supposed to go red. Shit on a stick. Alright, you got lots of X's there. Why? Oh! No. Okay, so this is not being driven. So none of these guys are driving the bus. Nobody's driving the bus. This guy is driving the bus, but he's only driving the part of the bus that we're interested in. So what's the problem? Do I have to connect all these lines? Would that change anything? I mean, I guess not having these lines connected might be causing this. Let's just connect the lines. Let's just do it. There's no harm in connecting these lines. These guys are now mutually... Your control buffer was connected to the queue. Where? This sounds like it's probably a big problem. My control buffer was connected to the queue. Is it? I don't think it is. Oh, it's supposed to be connected. No, it's connected to the queue from here. Yeah, it's fine. It's going into here. It's not connected directly. It should be fine. I think it's fine. It's not connected. Okay. Well, it's not connected now, and that's what makes me happy. Let's connect these guys here. Fast way of connecting. And let us see if this maybe... No problem. See you later, PutPixel. Okay, so this is good. This makes it so that nothing is nasty except... Well, this is undisconnected, but that's fine. It should be fine. It's not really the best, but it's fine. Alright, so this should work. Control T. Let's do this. Moment of truth. Moment of Control T. Toggle. Okay, good. We loaded into the blah. And we load. Okay, that worked. Now the moment of truth. Can we... Okay, we loaded that. That's fine. Can we store? We can store. And now 0, 0. What is instruction 0, 0 again? I believe that is move. Yeah, wait. 0, 0. Okay, that's load immediate into A. That worked. Let's add an instruction to move B into A. So we'll go to CPU control, move register to register. So that's destination source. So it's a 0, 1, so it should be 0, 1 hex. So we'll put a 0, 1 hex into here, I guess. 0, 1. Let's see if that works. So Control T should load 0, 1 into here. Yes. And then Control T should move this value into here. It works. Okay. So I believe now we have all of our instructions working. See you later, Hydrovolt. So we've got all of our instructions working now. And they're all working in one clock signal. So working super fast. And that's it. That is, I think this is probably all that we're going to have to deal with in terms of this part of the circuit. It's all set now. Now we can work on adding some more instructions. The only instructions we actually need in order to create a working computer that can execute a program is we need some math instructions, add and subtract. And we need some branching instructions. If we have those, we can make a Turing complete computer, or we would have a Turing complete computer. So let's do that. I don't like this. Okay, we're gonna connect these lines together. Let me think here. All right, I'm gonna use some thing that I didn't use in my original design, but that I probably should have. So there is a thing called a tunnel. And this should let us connect lines at a distance from each other. Oh shit. The tunnel is going to have to be... I'm not sure if I want to use the tunnel. Alright, so... Phase... opcode line. This is the phase reset line. Alright. I'm just going to do it the old-fashioned way. Connect these guys here. And... shit. Let's drag them over. Let's zoom... I don't want to zoom out too much because I won't be able to see. Darr! I need more room for my circuit, and I like to expand also into the width direction here. It's getting uglier as we speak. So we're just going to drag this way over off the screen. And how far do we want to go? We don't want to go that far. Actually, let's go back a little bit. Let's go back over to here maybe. Sweet. All right. Get rid of that. So we're going to create a little more space here to work with as we add our add and subtract instructions. Our arithmetics. There we go. That should be fine. And we'll just delete that. All right, so we want to do the same thing for this line here. This should be easier now. I can just zoom out and zoom out. Oh, I can't because I gotta, well, maybe. Fuck. All right, please let me select this. I think I did it. Hallelujah. And we'll put that one right about here. Drag this down here. We'll put this guy, I guess, over here, maybe. Stop it! Oh, did you connect? You better not have connected, you motherfucker. Why do you always want to do that? Okay, we'll start there. We'll grab it. No. Grab the line. There we go. Put that guy over there. And drag this guy over to here. Okay, so these are going to be, it's going to be round 2 here. Drag this up. I can zoom in a little bit. Make my life a little easier. Drag this guy up here. Drag this guy up here. There we go. All right. This is about the same as what we had over there. Now we want, what do we want? All right. So we want to put in our add and subtract instructions. So I guess first we've got to design what those are going to be. So instruction name. All right. Add, register to register or immediate. And the opcode is going to be 0001. So 0001 is going to be add and subtract space. And the opcode is going to be 0001. And we're going to make this a 1. Now I feel dirty. I feel like I'm not counting in the correct way. Let's cut this out. Put that down here. We're going to go subtract, register immediate. And here, 0001, 0. And this will be XXX. And over here, 0001, 0, X destination source. So I'm leaving one of these bits here reserved, and we'll talk about it later. Actually, set it to 0 for now. But it does mean something. We're going to be able to use this bit later on. But just forget about it for right now. So subtraction will be like this. Adding will be like this. And yeah, copy that, paste. There we go. So our add and subtract instructions. This is how they are going to look. Now the question is, actually, let's go to Chrome. And so now we've got to design the control bits for that bullshit. So add, let's go add register, actually, add or subtract register. At, where's my freaking at sign? There it is, at 0. All right. What I've just noticed is now, because I've revamped my instructions, this table here has become a little obsolete. But I'll figure it out later. For now, let's just work with what we got here. So if we want a register to register operation here, we can set load memory to 1. Select address, doesn't matter. Set it to 010. Increment IP. We want to set this one to 0 because we don't want to increment. We're going to get one increment when we load the opcode. We don't want to get another increment because this operation doesn't have any parameter data that follows the opcode. And load IP, that's a 0. Enable F. Enable F is a 1. No, 0. Enable F puts F onto the memory bus. That's bad. All right, enable flags. Now here, we want to enable our flags because this is an arithmetic operation, so it has to be able to affect the flags. What do we got here? ALU operation. Okay, this is the important part. This is going to be set to 0, 0, and here's another 0, but this 0 means that, where's that? That this bit is going to depend on the opcode. So add and subtract, one of the bits is going to control here to determine whether it's an add or a subtract instruction. And select X, select Y. Alright, this is important. X is going to be, let me think here. It's X minus Y, right? And it is destination minus source. So this has to be the destination. So, well, 0, 0, 0. 0, 0, 0. But we're going to make this red. There we go. So now one of the bits is going to control the operation, whether it's an add or subtract. And the source and destination bits are going to control these parts here. Enable A and enable B also controlled by the destination bit. So we gotta make, we're gonna make those red. And one more here. Make that red. Alright. Good times. So a lot of stuff is going to be controlled by our opcode here. And it seems about right. So what we're going to do is, first of all, let's just steal one of... What should we steal? Which one of these guys would be closest to what we want to do? Probably Control C, Control V. Maybe this guy? I don't know. Let's just use this guy anyways. So what we want to do is put you... Shit, I didn't do the thing with the lines. Put you maybe around here. Does that seem... maybe? Yeah, that seems plausible. For some reason, I made the order of these things backwards. I shouldn't do that. It's going to mess me up later. Let's put that like that. Connect this one to here. Connect this guy here. This has to connect to here. Good. And we also need the decoder line. That's going to be like this, sort of. Maybe like this. Copy that, paste it. Move that over here. To here. Seems good. All right. Connect that. Okay. So this is going to form the basis of our instruction. Don't like that. Let's change this. Let's zoom in so I can see what the hell I'm... too much. Where are we? Here. So what we want this one to be is add sub, register, register, or immediate. And put that there. Alright, now we need to... well, first off, we need to set this value here. So what we're going to do This is where this stuff is going to shine. So hopefully I haven't fucked anything up here. I don't think I have. Wait. First off, this is I named it wrong. It says this is a deceptive naming because it's just register to register. Yeah, we're gonna do it like that. All right, so let's take a look at this guy. We're gonna copy all of these guys here. Then we're gonna go to remove white space 2. Text mechanic, remove extra white spaces. There we go. Let's take, no wait, I am in Chrome. Okay, good. Paste that. Remove all spaces, go. Good. So now we have our binary number. Copy that. And going to here. 0B. All that bullshit. There we go. So there's our code in here. Hopefully that works. And now what we need to do is we need to figure out the parts that have to be configured based on the opcode. So those parts are select X, select Y, enable A, enable B, and the ALU operation. So I think, I don't know, select X, select Y, enable A, enable B. Let's go into Logisim here. Let's zoom in a little bit. Again, a nice big view on this mother. All right. So where are all of these fucking lines? First of all, I need it even bigger because I can't read those fucking numbers. Too small. All right, here we go. So let's go back. CPU control. So 0, 1. Actually, basically, we just need to break out everything to 10. And that'll be good. All right, that's easy to remember. Break out everything to 10. This does not need to be broken out. So get rid of that. Get rid of that. Connect that. Okay. So this needs to be broken out. This needs to be broken out. This, and this. All right. So let's see what bits. So the bits that we're interested in here are bit width out is 3. Just get rid of all this. All right. So the bits that we're interested in. And bit 0 is going to be, wait, I think actually I need more bits. No, I need 3 bits. So bit 0 is going to go to the top. Bit 1 is going to go here. And then bit 4, bit 3, where is it? This bit here, this guy right here is what controls whether it's add or subtract. So that guy is bit 3. Bit 3 goes to the bottom. Bit 2, none, 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 none. There we go. All right. Now to get to the nasty stuff. There's gonna be so many things to do. Maybe I need more space. Let's move this down to there. And let's drag this guy over here. Okay. So how do I want to do all this bullshit? Okay, these guys, I can just copy and paste them and use them again for all my other stuff. 8 to 10. All right. Wait. Oh, the numbers are at the bottom here. So that means that this one should be connected. That's fine. This guy here is going to meet up with his friend over there. Copy and paste. Put that there. Copy and paste. there. And what else? Drag that over a little bit. Drag this guy over here. There we go. We're all meeting in the middle. I think that's enough space to get all this bullshit out of here. Oh shit. Oh damn, it's that boy. Now I need more space. I'm gonna run out of space here. There's like too many things to break out. Alright. I am unhappy. Last week I went to a completely unrelated topic, but since I'm here just doing some bullshit, I went to Disneyland and it was alright. But fucking broke my phone again on the what is that ride? Not Splash Mountain. The Big Thunder Mountain. That's the one. Fucking smashed my phone all to hell. And because I smashed that phone like maybe about a year ago. And so I bought a replacement LCD and I tore the phone down and I fixed it. And it sort of worked for a while, but then it stopped working because my fucking glue job on the screen was bullshit. Maybe move this guy over here a little bit. So it finally stopped working like for good. And I'm like, okay, well, I'm going to do it good this time. And I put the screen back on, got it all on there. Sort of fucked it up again, but it was fine. And then I got onto Big Thunder Mountain and it fucking smashed my phone. So my phone doesn't work. Well, it sort of works, but like the top 20% of the screen, I can't do any touch controls on it. So it's kind of a problem. All right. I'm a big fan of do-it-yourself. My headphones just broke, so I stripped them open and reconnected the wires, which was a fucking big pain in the ass. Oh my god. But it works, and it saved me like $70. All right. 8 to 10, 5 to 7, 2 to 4, 0 and 1. So what do these guys mean again? Well, let's look at our Bible. 8 to 10 is the ALU operation. Okay, that's fine. So you are going to be set to whatever this is, but this guy has to be set to the value of bit 3 coming out of here, because that's the bit that tells us whether it's an add or subtract. So we pipe that guy into there and that's done. These guys are going to be the source and the destination. So the high bits are always going to be like that. Now, this is going to be, what is it going to be? Yeah, no, I am definitely aware of Louis Rossmann's stuff. I watched quite a bit of it, and it is pretty damn good. I have no problem with the electronics part. It's fucking like putting the case back together, the cell phone case that fucking messes me up every single time. The electronics works fine. But yeah, I do like Louis stuff. I'm a fan. All right. So, 5 to 7 is the X selector. X selection is controlled by X minus Y. So X is the destination, so that should be bit 1 here. Yes? So if it's 0, it's A. If it's 1, it's B. Yeah, I think that's right. I think that is correct. And then I can just do this, and maybe just like this. It seems too easy. Like, it seems like there's a catch. There's always a catch, isn't there? Oh, yeah. These guys are going to be a little more complicated. All right, so select, what are these guys? probably B and A, right? All right. So enable A, enable B. That's the destination controls that. So we destination U out here. And if this is set to 0, we want to set A to high. So we fucking... where's my NOT gate? Put a NOT gate in here. And we connect this like this. All right. So I think this is probably going to work. But who am I kidding? Get rid of that and that. Get rid of these guys. For shits and giggles. Okay, so this seems like it might be good. We got to test it. We obviously got to test this shit. So we want to... I want to clear this. We'll freaking clear the whole simulation. Reset simulation. And let's reset our circuit here. Alright, so let's load some values in. Let's do 7 minus 3. So, load 0, 0, 7 minus 0, 3. That's kind of complicated. 7 minus 5. 0, 5. There we go. And so we load the two registers, and then we do the subtraction, which is 7 minus 5, so it's be A minus B. I'm not going to do this in my head. I'm going to go to Chrome, opcodes. Let's see here. So, that would be a big 0, 0, 0, 1. Subtraction is 0. Then we just put a 0 in here, and we want destination is A minus B. So this is 1, 1. 1, 1 hexadecimal. All right, let's try that out. 1, no, you don't understand. 1, 1. Okay. I feel like this isn't going to work. I'm just really pessimistic here. I have good reason to be. There is precedent. Okay, let's do this. So, Control T. So we load 7 into A, we load 5 into B, and that didn't work. All right. Fuck. Why don't you work? There's got to be a reason. All right. This seems fine. This doesn't... It's got to be in here, right? I mean, it's got to be in here. It could be in here. Let's try this again. Reset. Clear that. All right. Please work. No, wait, it's not going to work. It's not going to work the second time, Chili. That's just not... That's... Einstein had something to say about that. Right. Alright, so if I clock it low, it's going to load this into here. And, okay, so here's the problem. First of all, this is not even connected. That just makes my face go like all scrunched up. Like, why is this not being driven? Because it should be driven. A whole bunch of things aren't being driven, which means, okay, I got it. I'm a dumbass. Forgot to fucking set the decoder on the instruction. It's probably not a good idea, right? All right, so what is this again? For my brain's sake, what are we decoding here? Let's look at the fucking thing here. All right, so these instructions 0001 is the thing. So we only want to decode 4 things. So we'll do that. And this one fan out is going to be 4. Bottom 2 1 0 none 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 none. There we go. There are 2 reasons why I like Louis Rossmann. Number 1, I mean, his videos are pretty fucking sweet. I like that shit. Number 2, the guy hates Apple, and so do I. I used to have an iPhone. Never again. Alright. I pissed off some people already. But that's okay. It's kind of my job. I mean, not really, but it's a job I take upon myself. Alright, here we go. Let's clock this mother. 0 da da da. Okay, we want to see what happens here. Yes. Okay, so we subtracted 5 from 7 and the result was 2. Success. Yes, 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 yes. Now we want to try to add some bullshit. So, let's see here. Okay, we're on the high. So we can change this. Oh, what is it? What is it? Fucking, I think it's going to be 1 1 9. 1 9 is going to do our job for us, I think. So, clock. Wait. Okay, that's good. And then clock again. And it should go back to 7. Yes, it goes to 7. So, we have successfully implemented register, add and subtract. Now we just got to do the same thing, but for immediate value. So, well, how much time we got? We still got like 30 minutes. That's plenty of time. We're not going to be able to finish the branching instructions, unfortunately. That's because those they're going to take a little bit, like more than 10 minutes to do. So, first off, we want this guy in our life. Copy that, paste it. Move that over there. Alright. Down here. And alright. So this is not going to be enough room, unfortunately. But the good news is I don't think we're going to need a phase 2 anytime soon. We kind of got rid of that stuff. Everything's now in phase 1. It's all about the phase 1. So, let's just do this. Get rid of this. That's not necessary. All right. So, let's see what we want. All right. So this circuit has to disable this. If these guys are the same, we disable. Actually, let's just fucking kill this right now. You go to hell, and you die. Put that there. Oh, no. Stop. Put that there. Put that there. Good. All right, now, this guy needs to disable this signal, because if we are doing an immediate move, then we're not doing a register to register. So, disabling is done with an AND gate. I don't want a 3 input. Why do you default to 3? Doesn't make any sense. Negate this one. So there, I will disable when this guy is high. There. And what else? What else do we want to do here? This guy has got to come in. Shit. We're going to go like that and like that. There we go. Okay. Now that we've got that all sorted, let's get our actual thing into here. So we're probably going to need basically the same stuff that we had for the other operation. So what we're going to do is copy this. Paste it. Move it over here. Move it on over to the west side. And you go like that. You go like that. I mean, sure. We don't technically need this guy, do we? These are going to be the same. So what we could do would drive you directly from there. There. Because either way, if we're doing this one or this one, we're going to have to reset the... I mean, for every instruction we're doing, we're resetting the thing, because we're never going into phase 2 or phase 1, depending on how you want to count it. So that's not a big deal. Ah, don't do that. Now we just got to figure out what's different between here and here. I mean, the operation is the same, right? Source. Okay, so the destination same, but the source now. The source, though. Source isn't important. All we care about is the destination, right? The destination bit, because the destination and the source, they're the same goddamn thing, first of all. So this is destination. Source we don't even care about. We're just going to get rid of that. Now here, the source is going to be set. It's going to be fixed, right? It's just going to be the what is it? The bus, the memory bus. That's going to provide the source, because this is going to be copy paste. Fuck, move that over there, and get rid of this here. Put this guy there. Fuck you. There we go. So immediate into register. There we go. All right. So it's mostly just going to be sorted out from here. Yeah, this chooses where the data goes. Oh yeah, X and Y. So, which is which? This is important. This is something we should probably think a little bit about before we just jump in there. Get rid of that. All right. So X has to be the data bus. So X is fixed. Y is the one that we're selecting. Is this good? Because subtracting is... Did I do it backwards? Because we have to... Y is the thing that we're subtracting. But we want to subtract the immediate value. Immediate value is on here. This is a problem. Should I have put the zeros in here on the X bus? Because if that's the case, I mean, I could probably just be lazy about this. It's definitely X minus Y, right? Because that previous operation worked. What we want is register into X, immediate value into Y. But Y currently does not have the option to select the immediate value, select the memory. So what we could do, so we could just do this. I mean, we've got a lot of inputs in here, but it's not what I want to do, because it's not strictly necessary to enable Y to use the immediate value. Eventually, we might end up filling these up, and in that case, we're going to regret using one of these multiplexer inputs for this. Decisions. How much time do I got left? I got 20 minutes left if I want to keep this within 2 hours. So, what I could do is I could rework. Let me just look into this. Just view that. All right. B. Yeah, I named it B and A here. Fuck me. B. Can you tell me where this? Can you tell me where? Get to Sesame Street. X. X is the bottom one. Now I'm confused. Yeah, X minus Y. Yeah, that makes sense. X minus Y. All right. Okay. So that is working as I figured it would work. Go back to computer. All right. So X minus Y. I want immediate into Y. So I can switch these up, but that means that I've got to fucking rewire. I got to renumber these instructions, and I don't want to renumber them. Fuck it. I might fix this off screen, but for now, I don't feel like it. So what I'm going to do is I'm going to make it so that you can pipe the memory into X or Y. You can do either. You could do both if you wanted. Be pretty stupid, but. Alright, so laziness wins over, but I might fix that later. So in that case, alright, back to what I was doing there before I so rudely interrupted myself. So X is got to be fixed to, no, X is not fixed. Let's just put this in here. The D bus is now 0, 0, 0, 1, 1. On there. So Y is fixed to the D bus. X is selected based on destination bit. Which one is which again? I keep fucking forgetting. So X is the first one, right? So destination bit fixes X and Y. Okay, so that's good. That is okay. Now, I believe that this should work. We've just got to figure out add sub register immediate. I don't really need these at zeros anymore because it's really only one phase. But future instructions might require multiple phases. For now, though, one phase fits all. Okay, so the selecting address is the same, load memory, same, increment IP has to be set to 1. Because now we've got an immediate that we need to increment for. Load IP, no. Enable F, no. Enable flags, yes. ALU operation, yes. Select X has got to be set to 0, 1, 0. That is non-negotiable. Select Y is set to destination. Enable A and enable B also selected based on the destination. This should work. So, copy that. Put it in here. Remove the spaces. Copy that. And put it in here. 0B. All that jazz. There we go. All right. This should work. I always say that. Let's try it out. No time like the present. So what we want to do is we want to load a value. Let's just clear this. Clear contents. Yes. Okay, so we're going to load a value into A, and then we're going to add an immediate value to that value. So 0, 0. Let's go with 66 hexadecimal. That looks like a 5. Is that a 5? Are you trying to mess with me? That's a 6. Okay. And then we're going to add to that. So, what is the... Shit. Where's my Chrome? Move extra space is this one. There we go. Opcodes. So immediate is going to be, okay, so they're both the same, and the destination is, so they got to be 0, 0 at the end. So it's going to be 0, 0, 0, 1, 1, 0, 0, 0. So 1, 8. 1, 8 is going to be add immediate value to register A. 1, 8 hexadecimal. And the value we're going to add is, of course, 3. Let's try it out. Cross fingers, commence finger crossing. Commence primary crossing. Here we go. Okay, so loaded 66 into A. So far, so good. Here we go. 69! We did it! We did it! Even worked on the first try. I did not expect that. I did not. So that's 1, 8. So if we add 3 to 8, that would be B. So 1B should be... Oh wait, that's to do it to register B. I don't want to do that. What I want to do is I want to subtract. So that would be... That would just be 1, 0, right? 1, 0. And subtract... I don't know. Subtract 60 hexadecimal. And we'll try this. So Control T. Control T. It didn't work. Didn't work, did it? That seems like it's a little wrong. Why? Why, oh why? Let's reset. Okay. Let's try this again. We'll move 66 into A. We subtract, we add 3 to A. Now if we push 10 into here, hexadecimal, that should activate our good old friend. Yes, you are active. And what else? What else is active? This is selecting the register that we're using for the operation. And this is selecting what again? No, this is selecting the operation itself, which is a subtracting operation, correct. This is selecting the register, which is A, correct. And this is selecting where the result is going to be stored, which is A, correct. So what's the problem then? Am I doing something weird? I want to subtract 60 from 69. The result should be 9. Should it not? What does this guy have to say? What do you have to say for yourself? Where's my probe? I'm going to probe you. Prepare to be probed. F7. That's not correct. Subtracting, that's not correct though. Why? 60, correct. Wait. 60? X minus Y. Why is 60 going up here? Why you gotta do me like that, bro? Did I fuck it up? I mean, obviously I fucked it up. Why? This should be, with the X selector, should be selecting our good old friend register A. And instead, it's not doing that. 69, it's flipped backwards. Flip turned upside down. Alright, well, I mean, that makes sense. Why it doesn't work, but why did I do that? Why is this? This guy is X, is he not? This is X, right? Let's go to CPU control. Let's check this out. Select X, ALU operation. Okay, yeah. ALU operation, select X, select Y. So ALU operation, select X. This is high. Oh, okay, so I fucked up my, my binary here. This shouldn't be high. This should be low. This one should be high. Let's, let us rectify that. Why is that? ALU operation, that's fine. Select X should be 0, 0 with our good old friend modifiable bit. And this one should be 1, 0. Better. Okay, so I was just fucked up something there. Not a big deal. We got this. We're solid. What do the kids say? 100? Keeping it 100? I don't know. I live in Japan. Doesn't affect me. Where is my... Here it is. Put that there. 0B pasty. Okay, now you should work. This one worked, right? Yeah, it worked. I had the right one there. I just had a brain fart in the other one. Alright, let's do it to it. 0, 16. Why is that 0? Right, because it's... Okay. Okay, sorry. I apologize. Obviously, this is D-bus is going to be 1, 1. I don't know what I was smoking. But I want some. There we go. Remove the white spaces. Copy that. And we go back over here. Circuit diagram is getting too big. Paste that in there. Okay. This should work. Let's take a quick look. See what the... yeah, 60 minus 9. Alright, good. Let's reset. I know, now we know it's going to work, but just for completionist's sake, let's run our dumb program here. So, Control T. We load... Wait, why... I said clear? Reset? Hello? Something... Yeah, that's fine. Control T. We load 66 into there. We add 3. Then we subtract 60. And the final result is 9. Hallelujah. We have it. Wait. Let me just try subtracting... well, here, we'll load. Let's do this here. We'll load 7 into register B, and then we'll subtract B from A, which is what? I just want to make sure my subtraction works in that one too. And subtract B from A, sub is going to be, let's just do this here, 0, 0, 0, 1, 0, 0, destination is A, 0, source is 1, so that's 11, that's what it was. I seem to recall that being an instruction that we used before. Alright, last dance with Mary Jane, one more time to kill the pain, is that how that goes? Toggle. So we load 66, we add 3, subtract 60, and then we load 7 into B, and if we subtract this from this, we should get 2. And then we get 2. So it's all good. We have achieved addition and subtraction. And we have all of our instructions running in a single clock cycle. And we double pumped our IP instruction pointer. I think we got a lot accomplished today. Not so much fucking up, which is always good. And that's weird. Well, I don't know what to tell you, Rob, because I can't see your circuit. But you can, if you try to debug it and you still can't get it to work, you can send it to me on the forum, and I'll take a look at it for you if you really can't get it working. I'll try to point you in the right direction there. But I don't know, it works for me. That sounds like a big... Yeah, you can do that. Oh yeah, that's true. You can just look at my circuit too. It's all good. But I think that's it for today. We're approaching the 2 p.m. my time, and it's time for me to maybe eat breakfast now at 2 p.m. I have a weird life, but anyways, thanks for coming out and saying hi in chat, and I will see you whenever I see you. Wait. Wait, why is it? I've lost this. I don't remember what I said. It's probably because I'm white. I don't understand, but okay, it's good. I too am a white guy. Chili pork unit. I really like that name. So I'll see you guys later. See, that doesn't make sense because I am also white. So, see, your logic is flawed there, Rob. I appreciate the sentiment. You have to own your white privilege, but still, that's not the problem. So, thanks for coming down, and I'll see you later.